Just a few more examples here. We're going to begin with an informal definition. Suppose f is defined for all x near a. If x gets sufficiently close to a and f of x gets arbitrarily large, then we write that the limit as x approaches a from both sides, the corresponding function values will approach a concept called infinity. And this infinity is not a finite number. In fact, this infinity just represents the concept of very large. In fact, you could think of infinity as very, 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 very large. So since infinity is not a finite number, we can also conclude that this limit right here does not exist. So that's a secondary conclusion. In a similar fashion, function values can approach very large in a negative direction. So practice reading this as limit notation. The limit, as x approaches a from both sides, the corresponding function values approach infinity in the negative direction, or negative infinity. We can similarly have definitions for one-sided limits. Look at the limit as x approaches a from one side or from the right side here. Where could the function values go? The function values could go to the concept of infinity. In a similar fashion, you could look at x approaches a from the left-hand side. Where can a function value go? Or where can we say the corresponding function values go? They can go towards infinity in the negative direction. Let's look at this using the examples from algebra that you know. So we're going to look at the natural log of x. And we could draw this function rather quickly, just a quick sketch. Doesn't have to be completely accurate, but you know that generally speaking, the natural log function looks like that with an x-intercept. And as x values approach 0 from the right, where do the corresponding y values go? As x values approach 0 from the right, where do the corresponding y values go? Let's do that one more time. As x values approach 0 from the right, the corresponding y values are going to a concept. In fact, they're going to the concept called negative infinity. So that's one conclusion. Remember, we could draw secondary conclusions. The limit as x approaches 0 from the right of the natural log of x simply does not exist. So that's a secondary conclusion. One more conclusion here. You know that from your algebra class, you have this vertical line. And this vertical line is now going to be represented in calculus. This is x equals 0. Therefore, that vertical line, x equals 0, is a vertical asymptote. It's a vertical asymptote of the function. Now remember, the function values cannot cross that vertical asymptote. Let's look at another example, an example from trigonometry. Go ahead and draw the tangent function. I'm going to go ahead and use NTS. Remember, what does NTS stand for? NTS stands for not to scale. If you were thinking of a Korean boy band, you were a little bit off there. Remember, this is pi over 2. This is the opposite of pi over 2. This right here is pi over 4. Over here, this is negative pi over 4. And we could draw a period of tangent. I'll leave it up to you to draw a second period. Now let's look at the x values. As the x values approach pi over 2 from the left, where do the corresponding y values go? The corresponding y values are going to a concept. They're going to the concept of positive infinity. So that's our first conclusion. Our second conclusion is that the limit as x approaches pi over 2 from the left of the function tangent of x does not exist. And what do you think our third conclusion is? Our third conclusion here says, therefore, what happens to this vertical line here? X equals pi over 2. This becomes our definition of a vertical asymptote. So it turns out the definition of a vertical asymptote involves limits. Whoa. Let's look at another example. Let's use the same picture and see if we could evaluate the limit as x approaches negative pi over 2 from the right. So as x approaches negative pi over 2 from the right, where do the corresponding function values go? They're going to the concept called infinity in the negative direction. So I'm going to write equals negative infinity. Very deceiving because infinity is not a finite number. Since it's not a finite number, we could conclude that the limit as x approaches negative pi over 2 from the right of tangent of x does not exist. And just like the previous other examples, what's our third conclusion here? Therefore, x equals negative pi over 2 is a vertical asymptote of the function. One more example here. We have a rational function, and we already know that from algebra, the domain here, x cannot equal 3. And if you remember how to graph this from algebra, you could draw a quick sketch. Once again, you could use NTS. Okay, remember NTS means not to scale. And you may have recalled that you drew some vertical lines before. You drew a vertical line here at x equals 3. You also could draw a vertical line, not a vertical line, but a horizontal line at y equals negative 5. Now clearly this is not to scale, okay? The hint here says use 29/10. Now remember 29/10 is about 2 9/10. So if you try to evaluate 2 9/10 of a function, if you plug in 2 9/10 in here, you start to gain some perspective of what the graph looks like. So 2 9/10. So I'm approaching 3 from the left. That's why we're picking 2 9/10. If you approach 3 from the left and you pick 2 9/10, 2 9/10, you'll have a negative numerator over a negative denominator. All right. Now what's happening is you have a concept. Okay. Let me see if I can write that concept for you. That concept is in a bubble. You have a negative numerator, negative large in the numerator over what? Negative small in the denominator. Now take a large number, let's say 1 million, and divide it by a very small number, like 1/100th. Well, what would you end up getting? You end up getting something very large, right? You get something huge. So a large number divided by a very small number, a small number less than 1, will actually get you a large number. So this gives you the idea that this is in fact approaching the concept positive infinity. as long as x is approaching 3 from the left-hand side. So I'm going to write that. It's approaching positive infinity as long as x is approaching 3 from the left-hand side. What's our secondary conclusion? The limit as x approaches 3 from the left of 2 minus 5x over x minus 3 does not exist. And our third conclusion, therefore, what is x equals 3? X equals 3 is now called the vertical asymptote of the function. Once again, what does this all mean? That means vertical asymptotes have a definition that is related to the idea of a limit. So what do examples 7 through 10 have in common? All these examples have a vertical asymptote, at least one, that is defined by looking at limits. Now the more formal definition is right there. So go ahead and rewrite that on your own, be able to read it, understand it, and of course use it in your graphical approach of looking at limits. So if the limit as x approaches a from the left or from the right or from both sides, and it approaches infinity or negative infinity, then we define x equals a to be the vertical asymptote of the function.